Something is moving through the darkness toward us right now. Not with the brutal speed of an asteroid, not with the predictable arc of a satellite, but with the patient, inevitable approach of something ancient awakening from the cosmic deep. Its name is C2025, R2, and it shouldn't be this bright. On September 11th, 2025, an instrument never designed to hunt comets accidentally stumbled across something extraordinary. The solar wind anisotropies instrument aboard the SOHO spacecraft, built to map hydrogen emissions at the edge of our solar system, detected a burst of activity where nothing should exist. A fountain of hydrogen-rich water vapor, erupting against the background of interplanetary space. The discovery was almost casual. Swan wasn't looking for comets. It was monitoring the solar wind, tracking the invisible river of charged particles streaming from our sun. But comets, it turns out, announce themselves through betrayal. As they fall sunward, they begin releasing water vapor in quantities detectable from millions of kilometers away. Swan essentially trips over new comets by watching for their hydrogen signatures erupting against the cosmic dark. Within days of discovery, amateur astronomers began reporting something unsettling. C2025 R2 wasn't behaving like typical long-period comets, making their first approach to the Sun. It was brightening too quickly. Its coma, the fuzzy atmosphere of gas and dust surrounding the nucleus, was expanding faster than models predicted. And most strangely, its tail structure was developing characteristics that challenged conventional understanding of comet physics. By mid-September, the comet had reached approximately magnitude 6, hovering right at the threshold of naked-eye visibility under dark rural skies. Observers equipped with binoculars or small telescopes began capturing images near the constellation Virgo, close to the bright star Spica and the reddish glow of Mars in the western sky after sunset. The comet's tail was growing longer and more structured with each passing night, creating the classic appearance that has inspired human imagination for millennia. But here's what should make you pause. Comets are notoriously fragile creatures. Unlike the solid rock and metal construction of asteroids, comets are essentially dirty snowballs, loose aggregations of ice, dust, and organic compounds held together by weak gravitational forces and frozen volatiles. As they approach the Sun, the same heating that creates their spectacular tails can also tear them apart entirely. C2025 R2 is walking a razor's edge between spectacular display and catastrophic disintegration. The physics behind this delicate dance involves temperatures and pressures that would seem mundane in earthly contexts, but become matters of life and death for these ancient wanderers. Water ice begins sublimating, transitioning directly from solid to vaporette, temperatures around -73 degrees Celsius. More volatile compounds like carbon dioxide and methane begin outgassing at even greater distances from the Sun, sometimes beyond Jupiter's orbit. As these materials sublime, they don't simply evaporate peacefully. They create jets of gas that can dramatically alter a comet's trajectory through non-gravitational forces. Picture a spacecraft firing its thrusters randomly in different directions, and you begin to understand why comet orbits are notoriously difficult to predict with high precision. What makes C2025 R2 particularly fascinating and potentially alarming is its rate of brightening. Astronomers measure comet brightness using magnitude scales where lower numbers indicate brighter objects. A drop of just 1 magnitude means the comet is producing 2.5 times more light. C2025 R2 has been climbing the magnitude scale faster than standard models predict for an object at its distance from the Sun. This accelerated brightening could mean several things, none of them boring. First possibility: the comet contains unusually large reservoirs of supervolatile isis compounds that remain stable only in the frigid depths of the outer solar system. As it encounters gradually increasing solar heating, these materials are sublimating explosively, carrying dust and debris in expanding clouds that reflect sunlight back toward Earth. The faster than expected brightening suggests we are witnessing activation of materials that haven't felt stellar warmth in potentially millions of years. Second possibility: the nucleus is rotating in a way that periodically exposes fresh, volatile-rich surfaces to solar radiation. Many comets develop insulating mantles of dust and processed organics that suppress sublimation. If C2025 R2's rotation is breaking through these protective crusts, each new exposure could trigger burst-like increases in activity. Third possibility: the one that keeps comet researchers awake at night. The nucleus is fragmenting. Internal stresses from differential heating, gas pressure buildup, or structural weaknesses could be causing the solid nucleus to crack and split. When this happens, the sudden exposure of pristine interior isis to solar radiation can create dramatic flare-ups in brightness that presage complete disintegration. The viewing geometry for C2025 R2 presents both opportunities and challenges that will define what humanity can learn from this visitor as it continues falling toward the Sun through October. The comet will become increasingly difficult to observe from Earth due to its proximity to solar glare in our sky. The weeks of peak heating when thermal processing might reveal the most about its composition and internal structure will occur largely hidden from ground-based telescopes, but patience will be rewarded. Earth's orbital motion will gradually improve the viewing geometry throughout late October and into November. By early November, C2025 R2 should emerge from behind the solar glare into prime observing position, potentially at its brightest and most active phase. If the comet survives perihelion intact, it may put on a display visible to the naked eye from dark locations worldwide. The constellation Virgo offers favorable viewing for both northern and southern hemisphere observers during autumn 2025 after sunset. As twilight surrenders to darkness, the comet should appear as a fuzzy patch of light with a visible tail stretching away from the Sun's position. Binoculars will reveal far more detailed the structure of the coma, multiple tail components, and possibly even jets of material erupting from the nucleus itself. Amateur astronomers worldwide are already mobilizing their equipment for what could become one of the most observed comets of the decade. The global network of comet observers, connected through online forums and observing organizations, maintains nightly vigils on interesting objects. Their images, when compared across time, reveal subtle changes in brightness, tail structure, and coma morphology that often escape detection by professional observatories focused on other targets. But C2025 R2 isn't just another pretty sight in the evening sky. It represents something far more profound, a pristine sample of conditions in the early solar system, preserved in deep freeze for billions of years, and now being processed in real time by solar radiation. Every spectrum captured, every brightness measurement recorded, every tail structure documented adds to our understanding of where we came from and what materials built the worlds we inhabit. The Comet formed in the Oort cloud, that distant reservoir of icy bodies extending perhaps halfway to the nearest stars, condensed from the same nebular materials that built the Sun and planets. But unlike Earth, which has been geologically processed, heated, differentiated, and transformed over 4.6 billion years, comets remain largely unchanged since their formation. They are cosmic time capsules, carrying chemical signatures of the early solar system locked in pristine condition. What makes comet observations particularly urgent is their brief window of peak activity. Unlike planets and asteroids that can be studied over multiple apparitions and decades, comets are one-time events. Once C2025 R2 swings around the Sun and heads back toward the outer solar system, it won't return for thousands or even millions of years. It survives at all. Many comets, discovered by Swan, never survived their first close encounter with solar radiation. They fragment into debris streams that produce brief meteor showers before dissipating entirely into interplanetary dust. Whether C2025 R2 will join this graveyard of disrupted comets or emerge intact from its solar encounter remains one of the central mysteries surrounding its current approach. That as September surrendered to October, and the comet continued its inexorable fall sunward, observers began noticing something else in their images, something that didn't quite fit the standard narrative of a simple Oort cloud comet making its first close approach to the Sun. The color was wrong. The first reports came from experienced comet observers who had spent decades cataloging the subtle hues and spectral signatures of these celestial wanderers. Something about C2025 R2's appearance was triggering. Their pattern recognition systems, that finely tuned instinct developed through thousands of hours staring at fuzzy patches of light against the starfield. The comet was developing a greenish glow. Now, green comets aren't unprecedented in astronomical history. In fact, they're relatively common. The color emerges from a specific molecule called diatomic carbon-2, carbon atoms bonded together, designated as C2 in spectroscopic notation. When solar ultraviolet radiation breaks apart organic compounds in the comet's coma, it liberates these carbon dioxide. They fluoresce in green wavelengths, creating the eerie glow that has made comets like C2022 E3 CTF famous in recent years. But the intensity and rapidity of C2025 R2's color shift was unusual. Within a week of mid-September observations, the green tint had become unmistakable in amateur photographs. Professional spectroscopy confirmed elevated C2 emissions far beyond what standard models predicted for a comet at this distance from the Sun. This wasn't just aesthetic curiosity. The green glow was telling us something profound about the comet's composition and the chemical processes occurring in real time as ancient Isas encountered stellar radiation for potentially the first time in millions of years. Diatomic carbon doesn't exist naturally in significant quantities. It forms through photodissociation, the breaking apart of larger organic molecules by ultraviolet light. The strong C2 signature in C2025 R2 suggested the nucleus contained unusually high concentrations of complex carbon compounds. These could include simple hydrocarbons like methane, more elaborate organics like formaldehyde, or even prebiotic molecules that might have played roles in the origin of life on early Earth. The implications stretched beyond pure chemistry into questions of planetary formation, and the delivery of organic materials to young worlds. Comets have long been suspected as crucial vectors for bringing water and organic compounds to the inner solar system during the heavy bombardment period 4 billion years ago. If C2025 R2 represented a pristine sample of this ancient chemistry, its greenish glow was literally illuminating the conditions that might have seeded life on our planet, but the color mystery deepened when detailed spectroscopic analysis revealed something unexpected in the emission line profiles. The standard suite of cometary molecules was present hydroxyl radicals from water for towed association, cyanogen giving a slight blue tint to the inner coma, ammonia derivatives in trace amounts. Yet the ratios were wrong. The relative abundances didn't match the patterns established by decades of comet observations. Water vapor, typically the dominant volatile in most comets, appeared suppressed relative to carbon dioxide and carbon monoxide. This placed C2025 R2 in a rare category of core-rich comets that might have formed in the coldest regions of the protosolar nebula, perhaps even in the scattered disk beyond Neptune's orbit where temperatures remained low enough for these supernovae to condense efficiently. The chemical fingerprinting took on additional urgency as observers began noticing temporal variations in the green intensity. The glow wasn't constant. It pulsed and flickered on timescales of hours to days, suggesting that the comet's rotation was periodically exposing different surface regions to solar radiation. Each active area apparently contained different mixtures of organic compounds, creating a heterogeneous nucleus with distinct compositional zones. This heterogeneity hinted at a complex formation history, rather than condensing uniformly from a well-mixed region of the protosolar nebula. C2025 R2 might have accreted from materials with diverse thermal and chemical histories. Perhaps it formed near a boundary region where different ice condensation zones overlapped, creating a nucleus that was part water, part CO storage, part organocriture, cosmic layer cake preserving records of varying conditions. In the early solar system, professional observatories worldwide began dedicating significant telescope time to capturing high-resolution spectra across multiple wavelengths. The James Webb Space Telescope, with its extraordinary infrared sensitivity, could potentially detect complex organic molecules that remain invisible to optical instruments. The Hubble Space Telescope contributed sharp, visible light imaging that resolved the coma structure down to scales of a few hundred kilometers. What emerged from this coordinated observation campaign was a picture of extraordinary activity. The comet wasn't just passively sublimating as solar heating increased. It was actively responding to radiation in ways that suggested internal structure and composition far more complex than the simple, dirty snowball model that dominated comet science for decades. Multiple jet structures were visible in processed images, each apparently sourcing from discrete active regions on the rotating nucleus. These jets weren't randomly distributed, they appeared clustered in specific longitude and latitude ranges, suggesting that the nucleus had distinct geological provinces with different volatile contents and activity levels. The dust-to-gas ratio measurements added another puzzle piece. Typically, comets produce roughly 1 kilogram of dust for every kilogram of gas sublimated from the nucleus, but C2025 R2 appeared to be releasing significantly more gas relative to dust, creating an unusually transparent coma where the central nucleus remained visible even during peak outgassing events. This gas-rich behavior could indicate either an unusually porous nucleus, gas to escape efficiently, without entraining much dust, a composition dominated by highly volatile ices that sublimate at temperatures where dust particles remain frozen and trapped in the surface matrix. As October approached and the comet continued brightening toward naked eye visibility, the astronomical community found itself confronting an uncomfortable question. Were they witnessing normal comet behavior in an unusually active object? Or was C2025 R2 doing something genuinely unprecedented? The answer mattered because it spoke to deeper questions about the diversity of small bodies in the outer solar system. If every comet that entered the inner solar system displayed such unusual characteristics, it would suggest that our current understanding of comet formation and evolution was fundamentally incomplete. But if C2025 R2 represented a genuinely rare outlier, then understanding what made it different could reveal entirely new chapters in the story of planetary system formation. The timing of its discovery, an approach, also raised intriguing correlations with other cosmic events unfolding during the same narrow temporal window. The September surge of near-Earth asteroid encounters, the twin nova explosions in southern skies, the Venezuelan earthquakes, all clustering around the same weeks that C2025 R2 was rapidly brightening and developing its eerie green glow. Coincidence? Almost certainly. But the human mind, finely tuned by evolution to detect patterns, even in noise, couldn't help searching for connections. Could solar activity be affecting multiple objects simultaneously? Was there some seasonal variation in space weather conditions that triggered enhanced outgassing in comets, while also potentially influencing seismic activity through mechanisms not yet understood? Or were we simply experiencing the statistical equivalent of multiple lightning strikes, improbable events that occasionally cluster through pure chance? The scientific method demanded rigorous separation of correlation from causation. Just because events occurred simultaneously didn't imply any physical connection between them. Yet the clustering felt significant, as if the cosmos was orchestrating some grand performance with multiple actors taking the stage during the same remarkable act as, say, 2025 R2 continued its fall toward the sun, its green glow intensifying with each passing night. Observers began preparing for the critical weeks ahead. The comet would soon enter the period of maximum solar heating, the crucible where its true nature would be revealed through either triumphant survival or spectacular disintegration. The question wasn't just whether humans would witness a brilliant, naked-eye comet gracing October and November skies. The question was whether this ancient wanderer, carrying chemical signatures preserved since the solar system's formation, would survive long enough to share its secrets with the instruments pointed skyward in anticipation. Because comets are fragile, and the sun is merciless. October arrived with the kind of anticipation that makes astronomers check their weather forecasts obsessively, and amateur observers begin planning dark sky trips months in advance. C2025 R2 was approaching the moment of truth, the point of closest approach to the sun where solar radiation would reach maximum intensity, and the comet's fate would be decided. The mathematics were unforgiving. By late October, the comet would pass within approximately 0.6 astronomical units of the Sun, roughly 90 million kilometers, closer than Venus orbits our star. At this distance, solar heating would intensify dramatically, driving sublimation rates to their peak and potentially exposing structural weaknesses that had remained hidden during the comet's long approach. Ground-based observers watching C2025 R2 throughout early October documented a steady increase in activity that confirmed everyone's suspicions. This comet was building towards something spectacular. The coma had expanded to over 100,000 kilometers in diameter, larger than Jupiter, creating a ghostly green bubble of gas and dust that dwarfed the tiny solid nucleus at its heart. Tail development was accelerating as well. Two distinct structures had become visible even in amateur telescopes. The ion tail, composed of electrically charged gas molecules, stretched away from the Sun in a narrow or straight stream that could extend for millions of kilometers. This tail glowed with a bluish tint from ionized carbon monoxide, responding in real time to variations in the solar wind like a cosmic windsock. The dust tail followed a broader, more curved path, tracing the comet's orbital trajectory. Sunlight reflecting off countless microscopic particles created a yellowish-white fan that grew more prominent as outgassing intensified. Careful measurements of the dust tail's curvature allowed researchers to estimate particle sizes and ejection velocities, building a detailed picture of the physical processes occurring at the nucleus surface. But it was the unexpected third component that captured the most attention. Several experienced observers reported a faint anti-tailor spike of material that appeared to point toward the Sun rather than away from it. This sunward projection wasn't a violation of physics, but rather a projection effect created when Earth's viewing geometry allowed us to see the comet's dust trail edge. Large particles ejected days or weeks earlier, too massive to be pushed efficiently by solar radiation pressure, created this optical illusion that seemed to defy the fundamental rule that comet tails always point away from the Sun. The anti-tail's visibility provided crucial data about the size, distribution of dust particles in C2025 R2's coma. Only grains larger than about 1 millimeter would remain on near-Keplerian orbits, close enough to the nucleus to create the observed geometry. This suggested ongoing ejection of substantial debris, indicative of active erosion or even localized fragmentation events on the nucleus surface. Solar observatories monitoring space weather conditions added another layer of complexity to the unfolding story. The Sun was approaching the active phase of its 11-year cycle, with increased sunspot numbers and frequent coronal mass ejections. These billion-ton clouds of magnetized plasma, when they swept past the comet's location, could dramatically enhance ion tail activity and even trigger disconnection events where magnetic reconnection severed the tail entirely from the coma. The possibility of observing Acme interaction with C2025 are two excited researchers who study the interface between solar wind and cometary material. Such events, while documented in previous comets, remained poorly understood. Would the comet's unusual composition, with its elevated carbon dioxide and organic content, respond differently to solar wind disruption than typical water-rich comets? As the comet approached mid-October, viewing conditions from Earth began deteriorating due to geometry. C2025 R2's position in the sky was moving closer to the Sun's overwhelming glare, making observations increasingly challenging. The critical window for detailed study was closing just as the comet entered its most active phase. Professional observatories ramped up their observation cadence, knowing that within weeks the comet would be lost to solar conjunction, the period when its angular separation from the Sun dropped below safe observing limits. Teams coordinated observations across multiple wavelengths, optical telescopes tracked coma structure and tail development. Infrared instruments measured thermal emission from warming nucleus ice. Ultraviolet spectrographs detected the hydroxyl radicals that marked water, and radio telescopes searched for molecular line emissions that revealed coma composition. The James Webb Space Telescope made a critical observation series in mid, using its near-infrared instruments to peer through the comet's dusty coma and potentially resolve the nucleus itself. Previous estimates had placed the solid body somewhere between 2 and 5 kilometers in diameter, large enough to be structurally robust, but small enough that thermal stresses from differential heating could potentially cause fracturing. JWST, single quotes, as infrared eyes detected something intriguing. Temperature variations across the coma that suggested non-uniform outgassing from the nucleus. The warmest regions, presumably the most actively sublimating areas, showed temperatures approaching 200 Kelvin, well above the point where water ice begins transitioning to vapor. These hotspots appeared concentrated in specific regions, supporting the earlier inference that the nucleus had distinct compositional provinces with varying volatile contents. Amateur astronomers, freed from the constraints of formal observation proposals and telescope scheduling committees, maintained nightly vigils on the comet. Their less sophisticated equipment couldn't match the spectral resolution or sensitivity of professional instruments, but their sheer numbers and dedication provided temporal coverage that no single observatory could achieve. The American Association of Variable Star Observers coordinated this citizen science effort, collecting magnitude estimates and images from hundreds of observers worldwide. Their data revealed short-term brightness fluctuations, outbursts lasting hours to days that might have gone undetected in the gaps between professional observation runs. Each outburst likely represented a breakthrough event, where subsurface gas pressure ruptured an insulating dust mantle, exposing fresh volatile rich material to solar radiation. The social media astronomy community contributed another dimension to the observation campaign. Real-time image sharing allowed observers to coordinate on interesting features, directing limited telescope resources toward transient phenomena that demanded immediate follow-up. When one observer in Australia noticed an unusual brightening of a jet structure in the comet's inner coma, within hours telescopes in Europe and the Americas were tracking the feature as Earth's rotation brought them into darkness. This global collaboration represented modern astronomy at its finest, expertise and instrumentation, working seamlessly with amateur dedication and numerical advantage, all unified by the common goal of understanding this ancient visitor before it disappeared back into the cosmic dark dot as October 20th approached. The comet's brightness peaked near magnitude 4.5, visible to the naked eye from dark locations. A fuzzy star-like object with a faint tail discernible in binoculars. Urban observers reported success in spotting it from moderately light-polluted suburbs, though the tail detail remained washed out by for millions of casual this might be their only opportunity to see an active comet without specialized equipment. The viewing instructions spread across astronomy forums and social media. Look west after sunset. About halfway between the horizon and zenith. Find Spica, the bright blue-white star in Virgo. The comet sits approximately 10 degrees to Spica's upper left, about the width of your fist held at arm's length. Through binoculars, the greenish coma and beginning of the tail should be apparent. Through a telescope at low magnification, the complex coma structure and multiple tail components revealed themselves in stunning detail, but experienced observers knew what was coming. Within days, C2025 R2 would slip into the solar glare, becoming progressively more difficult to observe as its angular separation from the Sun decreased below 30 degrees. The perihelion passage itself, the moment of maximum heating and maximum peril, would occur largely hidden from Earth-based telescopes, observable only by solar monitoring spacecraft positioned to view the comet against the starfield, rather than the Sun's overwhelming brightness. The question haunting every comet researcher was simple: would C2025R to survive? The last clear observations came on October 24th, when a network of solar observatories captured C2025R2, silhouetted against the chromosphere, the Sun's lower atmosphere. The comet appeared as a tiny dark speck with a faint teardrop-shaped shadow extending behind it, backlit by the solar disk's overwhelming radiance. Within hours, even these specialized instruments would lose track of the comet as it plunged deeper into the Sun's glare. For the next 3 weeks, humanity would be effectively blind to whatever was happening at PERIHELION. This observational blackout wasn't unprecedented. Many comets had disappeared into solar conjunction before emerging weeks later, either intact or fragmented into debris streams. But the timing felt particularly cruel for C2025 R2, just as solar heating reached its maximum intensity, just as the comet's nucleus would undergo its most extreme thermal processing, just as the answers to fundamental questions about its composition and structure might be revealed. Earth's telescopes fell silent. The frustration among researchers was palpable. Decades of technological advancement, billions of dollars invested in sophisticated instrumentation, and humanity still couldn't observe a comet during its most critical evolutionary phase simply because it happened to pass too close to the Sun's position as seen from Earth. But there were other eyes watching. NASA's Parker Solar Probe, designed to study the Sun's corona from closer distances than any previous spacecraft, happened to be in a favorable orbital position during C2025R2's perihelion passage, while the probe's primary instruments weren't optimized for comet observations. Its wide-field images could potentially capture the comet's tail structure and coma evolution against the background corona. The data would be crude compared to dedicated comet missions, but it would be something, a window into the hidden weeks that ground-based observers couldn't access. The Solar and Heliospheric Observatory, SOHO, continued its vigil from the L1 Lagrange point between Earth and Sun. SOHO's coronagraphs, instruments that artificially block the solar disk to reveal the fainter corona, had discovered over 4,000 sun-grazing comets during its decades of operation, while C2025R2 wasn't approaching nearly close enough to be considered a sun. SOHO's instruments might catch glimpses of its tail structure during the perihelion passage. Theoretical models attempted to predict what might be happening during these hidden weeks. Computer simulations tracked the comet's trajectory through regions of intense solar radiation and particle bombardment. As C2025R2 approached within 90 million kilometers of the Sun, solar flux would increase by a factor of 3 compared to Earth's distance. Surface temperatures on the nucleus could soar above 300 Kelvin warm, enough to sublimate not just the supervolatile carbon dioxide and carbon monoxide, but also substantial quantities of water ice. The sublimation rates predicted by these models were extraordinary. At peak heating, the nucleus might be losing several tons of material per second, ejecting gas and dust in powerful jets that could alter the comet's trajectory through rocket-like forces. If the nucleus harbored any structural weaknesses, fracture planes, compositional boundaries, or void spaces from previous sublimation episodes, the internal gas pressure building from this intense heating could potentially split the comet apart. Historical precedent offered both hope and caution. Comet LINEARC 1999 S4 had famously disintegrated during its perihelion passage in July 2000, fragmenting into dozens of pieces that rapidly faded from view. Comet Dünya'nın met a similar fate in 2011, breaking apart before reaching perihelion and never recovering. But other comets Hellbop, Neos had survived perihelion passages at similar or even closer distances, emerging intact and putting on spectacular displays for weeks or months afterward. The key variable appeared to be nucleus, structure and composition. Comets with more consolidated nuclei, bound together by sintered ice and containing fewer structural flaws, tended to survive thermal stress better than loosely aggregated rubble piles held together primarily by gravity and frozen volatiles. Which category did C2025 to fall into? The pre-perihelion observations offered conflicting clues. The heterogeneous composition with distinct regions showing different volatile abundance suggested a complex internal structure, possibly indicating a nucleus assembled from multiple smaller bodies during the solar system's formation. Such agglomerated structures often harbor weak points at the boundaries between different compositional units. However, the comet's ability to maintain coherent jet structures over weeks of observation suggested at least some degree of mechanical integrity. Completely fragile nuclei typically showed chaotic, outgassing patterns with rapidly evolving active regions as thermal penetration broke apart subsurface layers. C2025 R2's jets, while variable, maintained consistent positions tied to nucleus rotation, indicating stable source regions capable of withstanding thermal cycling. As October surrendered to November, the astronomical community entered a period of anxious waiting. Social media channels devoted to comet observations filled with speculation and predictions. Would C2025 to emerge from solar conjunction as a brilliant naked eye object, its nucleus fully activated by perihelion heating? Or would it reappear diminished, perhaps fragmented, slowly fading as its remaining volatiles depleted during the long trek back to the outer solar system? Some observers began planning for a third possibility, that the comet wouldn't reappear at all. Complete disintegration during perihelion would scatter the nucleus into a debris stream to diffuse to produce a visible coma. Earth might pass through this stream years later, producing a brief meteor shower as dust particles burned up in the atmosphere, the only epitaph for a comet that had traveled billions of kilometers only to vaporize mere millions of kilometers from its goal. The waiting period also provided time for reflection on what C2025 R2 had already revealed. The unusually high organic content, marked by the intense green C2 emissions, confirmed that at least some comets forming in the early solar system incorporated substantial quantities of complex carbon compounds. Whether these organics formed locally through chemical reactions in the protosolar nebula or arrived from the interstellar medium remained debated, but their presence in primitive solar system bodies supported scenarios where comets delivered prebiotic chemistry to early Earth. The unusual CO2 to H2O ratio placed C 2025 R2 in the rare category of comets that likely formed beyond Neptune's orbit, in the coldest regions where carbon dioxide ice could efficiently condense. This suggested a formation location in the scattered disk or inner Oort cloud regions that serve as fossil records of planetary migration during the solar system's youth. 4 billion years ago, when giant planets were still migrating and gravitationally scattering smaller bodies into distant orbits. C 2025 R2 was likely ejected from its birthplace, closer to the Sun into the deep freeze of the outer solar system. The data collected during September and October would keep researchers occupied for months or years, mining spectroscopic observations for chemical signatures and analyzing temporal variations in coma structure. But nothing would match the scientific value of post-perihelion observations. The comet survived to provide them. As November 15th approached, the first recovery attempts would begin. Professional observatories would start scanning the region of sky where models predicted C 2025 R2 should emerge from solar conjunction. The comet would still be at challenging solar elongation separations of only 2025 degrees from the Sun, requiring observations during twilight, when the sky was neither fully dark nor overwhelmed by daylight. Amateur astronomers prepared their equipment for dawn patrols, setting alarms for pre-sunrise hours when the comet might be glimpsed low in the eastern sky before dawn's light washed it out. The race was on to be the first to recover C 2025 R2 and determine its post-perihelion fate. Would they find a brilliant survivor, its nucleus stripped of dust mantles and exposing fresh ice that blazed with enhanced activity? Or would their telescopes reveal only a faint smudge, the ghost of a comet that had given everything to solar heating and now limped toward oblivion? The answer waited in the fire-bright crucible of perihelion, hidden behind 150 million kilometers of intervening space and the overwhelming glare of our star. November 16th, 2025, 5:47 a.m. local time. An amateur astronomer named Sarah Chen stood in the pre-dawn darkness of rural New Mexico, her breath forming clouds in the cold desert air. Her 8-inch Schmidt-Cassegrain telescope was pointed low toward the eastern horizon, tracking coordinates that should diff. The orbital calculations were correct, contained C 2025 R2. If it still existed. The sky was beginning its slow transition from black to deep blue, that treacherous window where faint objects become visible but remain vulnerable to the approaching sunrise. Chen had perhaps 20 minutes before the growing twilight would overwhelm anything dimmer than magnitude 7 or 8. Her camera's live view screen showed nothing but stars. She adjusted the telescope's position slightly, compensating for atmospheric refraction near the horizon. Still nothing. A knot of disappointment began forming in her chest. 3 weeks of checking weather forecasts, planning this observing session, driving 2 hours to escape light pollution, all potentially for nothing. Then her screen flickered. At first, she thought it was a hot pixel or cosmic ray strike on the camera sensor, but the feature persisted across multiple frames. A fuzzy patch of light, barely distinguishable from the background noise, sitting almost exactly where the predictions said C 2025 R2 should be. She increased the exposure time from 30 seconds to 60, allowing more photons to accumulate. The fuzzy patch brightened. Definitely real. Definitely extended. Not a star. And most importantly, definitely moving at the rate expected for the comet's orbital motion. C2025. R2 had survived, within hours of Chen posting her recovery images to the Comet Observation Database. Telescopes worldwide began confirming the detection. The comet had emerged from perihelion passage, battered but intact, still producing a visible coma and tail despite weeks of intense solar heating. Initial magnitude estimates placed it around 6.5 dimmer than its pre-perihelion brightness, but still within range of binoculars and small telescopes. Over the following days, as the comet's angular separation from the Sun gradually increased and observing conditions improved, a detailed picture of its post-perihelion state began emerging. The news was both reassuring and puzzling. The nucleus appeared intact, no obvious fragmentation into multiple components, no rapidly dispersing debris cloud characteristic of catastrophic disintegration. This was survival in its most fundamental sense. C2025, R2 had withstood the thermal crucible of perihelion and remained a coherent object capable of ongoing activity. However, the comet's appearance had changed dramatically. The intense green color that dominated pre-perihelion observations had largely faded, replaced by a more neutral whitish tone with only faint hints of the earlier C2 emissions. Spectroscopic analysis revealed the reason. The easily sublimated organics that produced the green fluorescence had been largely depleted during perihelion passage. What remained was the more refractory material water ice, silicate dust, and complex, organic compounds that required higher temperatures to volatilize. This depletion pattern told a story of selective processing. The outer layers of the nucleus, enriched in volatile compounds that sublimated readily, had been stripped away during perihelion heating. What observers were now seeing was deeper material, perhaps ice that had been buried beneath insulating dust mantles and only now was becoming exposed to solar radiation as the surface eroded. The tail structure had evolved as well. The ion tail, while still present, appeared shorter and less structured than before. This suggested reduced gas production rates. The nucleus was no longer releasing volatiles at the furious pace that characterized its approach phase. The dust tail remained prominent, curved gracefully along the comet's orbital path, but it too showed signs of diminished activity. Yet despite these indicators of decline, the comet was far from dead. High-resolution images revealed that discrete jets were still active, erupting from specific locations on the rotating nucleus. These jets appeared more concentrated than the diffuse outgassing observed suggesting that active regions had become more clearly defined as surface. Mantling preferentially preserved ice in some areas while exposing it in others. The rotation period analysis provided additional insights. Pre-perihelion observations had struggled to determine a precise rotation rate due to the comet's high activity and complex light curve. But now, with reduced overall brightness and more distinct jet features, researchers could track specific structures as they rotated in and out of view. The period appeared to be approximately 12.7 hours, reasonably typical for a comet nucleus in the 2 to 5 kilometer size range. But more intriguingly, the light curve showed variations suggesting an elongated shape rather than a spherical nucleus. The brightness changed by nearly half a magnitude over each rotation cycle, indicating that the nucleus presented different cross-sectional areas to observers as it spun. This elongation might explain some of the comet's unusual pre-perihelion behavior. An elongated nucleus with distinct compositional regions on different parts of its hot surface could produce the heterogeneous outgassing patterns that had puzzled researchers. As different faces of the nucleus rotated into sunlight, they would activate preferentially, creating the temporal variations in brightness and spectral signatures observed throughout October. Professional observatories ramped up their post-perihelion observation programs, eager to document the comet's continued evolution. The James Webb Space Telescope obtained another series of infrared spectra, revealing that while the easily detected volatiles like CO2 and organics had diminished, water vapor production remained relatively strong. The comet was transitioning from a CO2-dominated to a H2O-dominated object as its surface composition evolved through selective depletion. This transition provided a natural laboratory for studying how comets age and evolve over multiple perihelion passages. Long-period comets making their first approach from the Oort cloud typically show pristine surface compositions reflecting their formation conditions. But after perihelion passage, they've been thermally processed, their surfaces stripped, reorganized, and depleted in the most volatile species. C2025 R2 was essentially fast-forwarding through an aging process that might take multiple orbits for short-period comets that return every few years. Hubble Space Telescope contributed crucial observations of the inner coma structure. HST's sharp imaging revealed complex spiraling patterns in the dust distribution, likely created by the combination of nucleus rotation and discrete jet activity. These spiral structures, sometimes called Archimedes spirals, encode information about rotation rates, jet orientations, and the timing of outburst events. One particularly intriguing feature appeared in multiple HST images: a bright knot of material in the inner coma, offset slightly from the nucleus position. This knot might represent a concentration of large dust particles, or small boulders ejected during perihelion passage, perhaps fragments that had broken off the nucleus due to thermal stress but remained gravitationally bound or had insufficient velocity to escape completely. If this knot represented genuine fragmentation, it raised questions about the nucleus's structural integrity. Had C2025 R2 suffered internal damage during perihelion that might lead to more substantial breakup in the future? Or was this simply normal erosion, the expected consequence of intense heating and sublimation pressure acting on a loosely consolidated icy body? Amateur observers continued their nightly vigils, documenting the comet's gradual fading as it receded from both the Sun and Earth. By late November, C2025 R2 had dimmed to magnitude 7.5, still detectable in modest telescopes, but no longer a naked-eye object. The tail, while still visible, had shortened considerably as gas and dust production rates declined with increasing solar distance. The viewing geometry was improving, though, as Earth's orbital motion and the comet's trajectory carried them along their respective paths. The angular separation between C2025 R2 and the Sun continued increasing. By early December, the comet would be observable throughout the night rather than just during twilight hours, providing optimal conditions for long exposure, photography, and detailed spectroscopy. This extended observation window represented the final opportunity to extract maximum scientific value from C2025 R2's apparition. Within months, the comet would fade beyond the reach of all but the largest professional telescopes. Within a year, it would disappear entirely into the cosmic dark, beginning its long journey back to the outer solar system, where it might orbit for thousands or millions of years before, perhaps making another approach to the Sun. The survival of C 2025 R2 through perihelion answered one fundamental question while raising dozens more. What was it about this particular comet's structure and composition that allowed it to remain intact through thermal stresses that had destroyed so many others? December arrived with the kind of crystalline clarity that astronomers dream about: cold nights, stable atmospheres, and C 2025 R2 positioned perfectly in the pre-midnight sky for extended observation sessions. But as telescopes worldwide tracked the comet's gradual recession from the inner solar system, they began documenting something that hadn't been predicted by any model: unexpected fluctuations in the ion tail that seemed to correlate with solar activity in ways that challenged conventional understanding. The ion tail of a comet represents one of nature's most elegant demonstrations of electromagnetic forces at work. Unlike the dust tail, which follows a curved path determined primarily by solar radiation pressure and orbital mechanics, the ion tail stretches directly away from the Sun along magnetic field lines embedded in the solar wind. These tails can extend for tens of millions of kilometers, creating visible manifestations of otherwise invisible magnetic structures pervading interplanetary space. C 2025 R2's ion tail had been relatively quiescent during late November, showing the expected blue-tinted glow from ionized carbon monoxide molecules fluorescing under solar ultraviolet radiation. But in early December, ground-based observers began noticing rapid variations in tail brightness and structure that occurred on timescales of hours rather than days. High-cadence imaging revealed the culprit. The comet was experiencing repeated interactions with structures in the solar wind, not the dramatic disconnection. Events that had been observed in famous comets, like entire ion tails separated from the coma and drifted away, but rather more subtle ripples and waves propagating through the tail structure as varying solar wind conditions swept past the comet's location. These variations weren't random. Solar physicists analyzing space weather data from the ACE and DSCOVR spacecraft positioned at the L1 Lagrange point noticed a correlation. Each time these monitors detected a change in solar wind density or magnetic field orientation, within hours, C 2025 R2's ion tail would respond with corresponding brightness fluctuations or structural reorganization. The comet had become a giant windsock for space weather. This wasn't merely a curiosity. The interactions provided researchers with a unique opportunity to study magnetic reconnection, the process where magnetic field lines from different sources connect, disconnect, and reconnect, releasing energy and accelerating particles in the process. When the interplanetary magnetic field embedded in the solar wind encountered the magnetic field draped around C 2025 R2's ionosphere, reconnection events occurred at the interface, creating the waves and disturbances visible in the ion tail. Understanding these reconnection processes had implications far beyond comet science. The same physics operates in Earth's magnetosphere during geomagnetic storms, in the Sun's corona during solar flares, and in the accretion disks around black holes. C 2025 R2 was providing a natural laboratory for studying magnetic reconnection under conditions that couldn't be replicated in terrestrial experiments. But The most intriguing aspect of these observations emerged when researchers began comparing the timing of the comet's ion tail fluctuations with terrestrial phenomena. A postdoctoral researcher at the European Space Agency, analyzing data from both comet observations and ground-based noticed something peculiar. Some of the ion tail disturbances appeared to precede detectable changes in Earth's magnetic field by several hours. This seemed backwards. If both the comet and Earth were responding to the same solar wind structures, they should react simultaneously or more precisely, with a delay determined by the time required for solar wind to travel from the comet's position to Earth's location. But some events showed the opposite pattern. With the comet responding first, the explanation required careful consideration of geometry and solar wind structure. The solar wind doesn't flow uniformly like water from a faucet. It contains structure faster and slower streams, regions of enhanced density, and magnetic field sectors with different orientations. These structures are organized on scales of millions of kilometers, meaning that depending on the relative positions of Earth and the comet, they might encounter different parts of the same large-scale solar wind feature at different times. If C2025 R2 happened to be positioned upstream of Earth relative to the solar wind flow direction, it would encounter incoming structures first, providing an early warning of space weather conditions that would later affect our planet. This positioning essentially turned the comet into a natural space weather monitoring station, complementing the spacecraft-based systems that provide similar forecasting capabilities. Amateur observers contributing to international comet observation networks found themselves inadvertently participating in space weather research. Their nightly images of C2025 R2, originally intended simply to track the comet's brightness and tail development, were being analyzed for temporal variations that correlated with solar wind measurements and geomagnetic activity indices. This unexpected crossover between comet science and space weather physics highlighted how interconnected different domains of solar system research had become. A comet discovered by an instrument designed to study hydrogen emissions in the solar wind was now being used to diagnose the structure of that same solar wind, while also providing insights into magnetic reconnection physics relevant to understanding space weather impacts on Earth. The December observations also revealed another surprise. C2025 R2 was experiencing what appeared to be a secondary activation phase. Despite being well past perihelion and moving outward from the Sun, the comet's brightness stabilized around magnitude 8, rather than continuing to fade as expected. Spectroscopic monitoring showed that water vapor production remained relatively constant even as solar heating decreased with increasing distance. This sustained activity suggested that the perihelion passage had fundamentally altered the nucleus surface. The intense heating had likely stripped away insulating dust mantles from extensive areas, exposing relatively pure water ice that could continue sublimating efficiently even at greater solar distances, rather than the rapid decline that often follows perihelion for first-time visitors from the Oort cloud. C2025 R2 was settling into a quasi-steady state of moderate activity. The implications extended to predictions about the comet's long-term evolution. If substantial areas of the nucleus now consisted of exposed water ice, the comet might remain active for months as it slowly receded from the inner solar system. This extended active phase would provide opportunities for continued observation and study well into 2026. Professional Observatories adjusted their observing schedules accordingly. What had been planned as a brief post-perihelion characterization campaign extended into an ongoing monitoring program that would track the comet's activity evolution over its entire outbound journey through the inner solar system. The Hubble Space Telescope obtained another series of higher resolution images in mid-December, revealing that the bright knot of material detected in November had evolved into multiple smaller concentrations, distributed along a linear chain. This structure strongly suggested that the knot had been a fragment that subsequently broke apart into several pieces, each now following nearly identical orbits slightly separated from the main nucleus. The fragmentation wasn't catastrophic. The primary nucleus remained intact and active, but it demonstrated that C2025 R2 had not emerged from perihelion completely unscathed. The thermal stresses and sublimation forces had been sufficient to dislodge at least one substantial fragment, and possibly others too small or faint to detect at the comet's current distance. This partial fragmentation raised questions about the nucleus's future structural integrity. Would continued thermal cycling as the nucleus rotated in different regions, experienced varying levels of solar heating lead to additional fragmentation events? Or had the perihelion passage essentially pruned the weakest structural elements, leaving a more consolidated nucleus that would survive future perihelia intact? The answer would remain unknown unless C2025 R2 somehow returned to the inner solar system, unlikely given its long orbital period that might extend for thousands of years or more. This single apparition represented humanity's only opportunity to study this particular object in detail. As December progressed toward the year's end, C2025 R2 continued its slow fade into the cosmic background. The tail, while still visible in modest telescopes, had shortened to a fraction of its pre-perihelion glory. The green color was now entirely absent, replaced by the neutral whitish glow of sunlight, scattered from dust particles and reflected from water ice. The comet was becoming ordinary, or rather, it was revealing what ordinary actually means for these ancient wanderers. The spectacular displays, the unusual colors, the rapid brightening that had captured public attention represented just one phase of comet evolution. The dramatic awakening as pristine surface materials encountered intense solar radiation for the first time. What remained was the baseline state, a moderately active comet slowly processing through its volatile inventory, gradually shrinking as sublimation carried away material that would never return. By late December 2025, C2025 R2 had faded to magnitude 9.5, still detectable in 6-inch telescopes from dark sites, but no longer the prominent evening sky object that had captivated casual observers in November. The comet was transitioning from public spectacle to scientific dataset, its future observations restricted to dedicated amateur astronomers and professional research programs with access to large aperture instruments. Yet even as the comet receded from easy visibility, the questions it raised grew more insistent. The first question was compositional. Why did C2025 R2 display such unusual chemistry compared to the broader population of Oort cloud comets? The elevated carbon dioxide ratios and intense organic content suggested formation conditions unlike those that produced typical comets in our solar system. Several competing hypotheses emerged from the data. Hypothesis 1 proposed that C2025 R2 formed in an unusually cold region of the protosolar nebula, perhaps during an early phase when the young sun's luminosity was lower than its current value. Under these frigid conditions, carbon dioxide would have condensed more efficiently relative to water, producing the observed compositional anomaly. This scenario required specific timing. Formation had to occur before the sun's luminosity increased to its main sequence value, providing a narrow temporal window, perhaps lasting only a few million years. Hypothesis suggested that the comet's formation location was simply farther from the sun than typical Oort cloud objects, placing it in the scattered disk or detached population beyond Neptune's orbit. In these distant regions, where temperatures remain below 40 Kelvin even today, carbon dioxide and other supervolatiles dominate the ice chemistry. Subsequent gravitational perturbations could have ejected the comet into a long-period orbit that eventually brought it into the inner solar system billions of years later. A third, more speculative hypothesis proposed that C2025 R2 might not have formed in our solar system at all if the sun had captured the comet during a close encounter with another star system during the solar system's youth, when the sun was still part of its birth star cluster. The object could carry compositional signatures reflecting formation around a different star with different chemical abundances. This interstellar capture scenario was controversial and difficult to prove. It required very specific dynamical conditions during the solar system's first few million years, when gravitational interactions were chaotic enough to enable capture of bodies from passing stellar systems. Most dynamical studies suggested such captures should be extremely rare, perhaps occurring only once per 1,000 stellar encounters. But rare didn't mean impossible, and C2025 R2's unusual chemistry provided circumstantial support for exotic origins. The second major question concerned structural evolution. The partial fragmentation observed during perihelion passage demonstrated that the nucleus wasn't a monolithic solid body, but rather a more loosely consolidated aggregate. Yet it had remained intact through thermal stresses that destroyed many other comets. What gave C2025R to sufficient structural integrity to survive? High-resolution modeling of thermal stress distributions within comet nuclei suggested that size played a crucial role. Nuclei smaller than about 1 kilometer tend to fragment easily because thermal gradients can penetrate deeply, creating internal pressure that exceeds the weak gravitational and cohesive forces holding the body together. Nuclei larger than several kilometers have enough self-gravity to resist disruption even when internal sublimation generates substantial gas. Pressure C2025R2, with its estimated 2 to 5 kilometer diameter, sat in the transitional size range where survival depended on specific structural details. A nucleus with moderate strengths, perhaps partially sintered ice, creating weak cementing between grains, could survive where a purely gravitational aggregate might fail. The OBSERVED fragment separation provided additional clues. The fact that fragments remained on nearly identical orbits rather than rapidly diverging suggested they were ejected with relatively low velocities, perhaps only a few meters per second. This implied that the fragmentation occurred through gentle separation rather than explosive disruption, more like carving from a glacier than detonation of a brittle solid. The third question was perhaps the most intriguing. What role, if any, did C2025R2's arrival play in the broader context of September 2025's remarkable clustering of cosmic events? The statistical arguments were clear. Given the number of near-Earth asteroids, the frequency of nova explosions, the regular occurrence of earthquakes in tectonically active regions, and the expected rate of comet discoveries. Having all these phenomena cluster within a few weeks wasn't impossible, just improbable. Calculating the exact probability required careful consideration of selection effects and observational biases. More sensitive surveys naturally detected more objects, creating the impression of increased activity even when the underlying population remained constant. Social media and instant communication amplified awareness of each individual event, making the clustering seem more remarkable than it might have appeared to astronomers working in pre-internet isolation. Yet even accounting for these biases, the September-October 2025 period stood out. Multiple independent lines of evidence suggested a genuine excess of activity beyond baseline expectations. Could there be physical connections between these apparently disparate phenomena? The scientific mainstream remained skeptical. No demonstrated mechanism linked stellar explosions thousands of light-years away with terrestrial seismic activity. Solar activity affected Earth's magnetosphere and upper atmosphere, but claims of space weather influencing earthquake occurrence remained unproven despite decades of investigation. C2025. R2's role in this clustering was particularly ambiguous. As a comet originating from the outer solar system, it had no causal relationship with near-Earth asteroids following entirely different orbital paths. Its perihelion passage timing was determined by gravitational dynamics established when it was ejected from the Oort cloud, potentially millions of years ago, before any of the September events could have influenced its trajectory. The correlations, if they meant anything beyond coincidence, would require mechanisms operating on scales and through channels that current physics didn't recognize. This didn't make such mechanisms History was filled with phenomena once dismissed as impossible that later became mainstream. Understanding, but it demanded extraordinary evidence before extraordinary claims could be accepted. A more prosaic explanation involved anthropic selection. Humans naturally remember remarkable confluences of events more vividly than mundane periods where nothing special occurs. The September 2025 clustering might simply represent the rare but inevitable outcome of random processes operating over long timescales. Given enough time, unlikely combinations of events must occasionally occur. The fourth question concerned prediction and preparation. Could the insights gained from C2025 R2's apparition improve our ability to forecast the behavior of future comets? The answer was nuanced. Each comet remained fundamentally unique, a product of specific formation conditions, evolutionary history, and structural characteristics that couldn't be fully known until detailed observations were obtained. But patterns were emerging from the growing dataset of well-observed comets. Composition appeared to correlate with formation location, with CO2-rich comets likely originating from colder, more distant regions of the protosolar nebula. Structural integrity seemed related to nucleus size and thermal history, with larger, more consolidated bodies more likely to survive perihelion passage intact. Activity evolution followed predictable patterns once surface properties and volatile inventories were characterized. These insights would inform preparation for future bright comets. When the next long-period comet was discovered inbound from the Oort cloud, astronomers could use its initial spectroscopic signatures to make educated guesses about likely behavior during perihelion passage. This forecasting ability had practical value for planning observation campaigns, allocating telescope time, and managing public expectations about potential. Naked eye visibility. The fifth and final question was perhaps the most profound. What did C 2025 are to teach us about our place in the cosmic order? Every comet that enters the inner solar system carries material preserved since the solar system's formation. A 4.6 billion-year-old time capsule documenting conditions when the Sun was young and Earth was still accreting from the swirling debris of the protoplanetary disk. The water molecules sublimating from C 2025. R2's nucleus might have originated in the interstellar cloud that collapsed to form our solar system. The organic compounds creating its green glow could be chemical cousins to the prebiotic materials that eventually led to life on Earth. We are, in a very literal sense, made of comet stuff. The water in our oceans, the carbon in our bodies, the nitrogen in our atmosphere all arrived through bombardment by objects like C 2025. R2 during Earth's violent youth. Studying comets meant studying our own origins, tracing the chemical pathways that led from interstellar clouds to living, thinking beings capable of turning telescopes skyward to observe their ancient cousins. This perspective transformed C 2025. R2 from a simple astronomical object into something more profounder, messenger from the deep past, a sample of the raw materials that built worlds, a reminder that Earth was not separate from the cosmos but intimately connected to processes, operating across billions of years and trillions of kilometers. January 2026 arrived with C 2025R to fading past magnitude 11. Visible only in telescopes of 8 inches aperture or larger from pristine dark sites. The comet was now receding from both the Sun and Earth, beginning its long journey back toward the outer solar system, where it would spend thousands or millions of years in cold storage before perhaps making another approach to the inner planets. For most casual observers, the comet's story had ended. The brief weeks of naked eye visibility in October and November were over. The social media posts had stopped, and public attention had moved on to other celestial events. But for the researchers, who had tracked C 2025 R2 through its entire apparition, the real work was just beginning. Terabytes of data awaited analysis. Spectroscopic observations spanning ultraviolet through infrared wavelengths contained chemical fingerprints that would take months to fully interpret. Higher resolution images from Hubble and ground-based adaptive optics systems revealed coma structures and nucleus features requiring detailed modeling to understand. Photometric measurements from hundreds of amateur observers needed to be compiled, calibrated, and analyzed for temporal patterns that might reveal rotation periods, outburst timing, and activity evolution. The scientific papers would emerge slowly over the following years. First would come the rapid response publications documenting basic observational results, the discovery, brightening curve, spectroscopic detections, and perihelion survival. These papers established the fundamental facts that later work would build upon. Then would come more detailed studies analyzing specific aspects of the comet's behavior. Teams would publish models of nucleus structure constrained by observed fragmentation patterns. Chemical analyses would attempt to determine formation temperatures and locations based on volatile ratios. Dynamical studies would trace the comet's orbit backwards through time, trying to determine when it was ejected from its birth location and what gravitational perturbations had shaped its journey. Some questions would find answers, others would remain open, waiting for better data from future comets or new theoretical insights that might illuminate. C C2025 R2's behavior in retrospect. But beyond the scientific publications and conference presentations, C2025 R2 left another legacy, one measured in inspiration rather than citations. Thousands of people had pointed binoculars or small telescopes toward the comet during its weeks of visibility, perhaps experiencing for the first time the profound connection that comes from observing a cosmic visitor with their own eyes, rather than through processed images on screens. Some of those observers would become dedicated amateur astronomers, investing in better equipment and learning the skills needed to contribute meaningful observations to the scientific community. A few might even pursue professional careers in planetary science or astronomy, inspired by the wonder they felt watching that fuzzy green patch move against the stars. Sarah Chen, whose recovery observation on November 16th had confirmed the comet's survival, found herself fielding interview requests from astronomy podcasts and magazines. She hadn't expected to become briefly famous for photographing a dim, fuzzy object before sunrise, but she embraced the opportunity to share her passion for comet observing with wider audiences. Her story resonated because it exemplified the democratic nature of modern astronomy. You didn't need a PhD or access to mountaintop observatories to make meaningful contributions. A modest telescope, clear skies, patience, and dedication could place you at the forefront of discovery. The first human to confirm that an ancient visitor from the outer solar system had survived its encounter with our star. The educational value of C2025 are too extended into classrooms worldwide. Teachers use the comet as a case study for lessons on orbital mechanics, spectroscopy, solar system formation, and the scientific method itself. Students learned to distinguish between observation and interpretation, data and models, facts and hypotheses, critical thinking skills that transcended astronomy into broader scientific literacy. The comet also served as a catalyst for discussions about planetary defense and near-Earth object tracking, while C2025 R2 posed no threat to Earth. Its discovery by the SOHO spacecraft's Swan instrument highlighted both the sophistication and limitations of current detection systems. We could detect comets millions of kilometers away through their hydrogen emissions, but we remained vulnerable to objects approaching from the direction of the sun or discovered too late for meaningful response preparation. Public interest in planetary defense had grown substantially since the successful DART mission demonstrated humanity's ability to deliberately alter an asteroid's trajectory. C2025 R2's apparition arrived during a period of increased funding for near-Earth object surveys and deflection technology development. The comet reminded policymakers and the public that our solar system remained an active, dynamic environment, where surprising visitors could arrive with relatively little warning. As winter deepened into 2026 and C2025 R2 continued its slow fade, the astronomical community began anticipating the next bright comet. Statistical models suggested that a naked-eye comet should appear every few years on average, though the actual intervals were highly variable. Some decades saw multiple bright comets, while others remained frustratingly barren. The next discovery could come at any time, perhaps tomorrow, perhaps not for several years. But whenever it arrived, astronomers would be better prepared, thanks to lessons learned from C2025 R2. They would know to obtain early spectroscopy to characterize composition and predict likely behavior. They would coordinate observation campaigns to maximize temporal coverage and wavelength diversity. They would engage amateur observers as partners, rather than merely enthusiasts, recognizing the critical role that dedicated individuals play in maintaining continuous monitoring that professional observatories cannot provide. The final observations of C2025 R2 came in late February 2026, when large professional telescopes pushed the detection limit to magnitude 13. Beyond this threshold, the comet faded into the background noise of the universe, still there, still active, but too faint for even the most powerful instruments to distinguish from the countless dim galaxies and distant quasars that populate the deep sky. The comet's trajectory would carry it outward past Mars's orbit by mid-2026, beyond the asteroid belt by 2027, past Jupiter's orbit by 2028. It would cross Saturn's orbit sometime in the 2030s, gradually slowing as the Sun's gravity fought against its outward motion. Eventually, perhaps decades from now, it would reach aphelion, the farthest point from the Sun, and begin the long fall back inward. Whether that return journey would bring it back to the inner solar system within human timescales remained uncertain. Orbital calculations were precise for the near term, but grew increasingly uncertain when projected thousands of years into the future. Gravitational perturbations from passing stars, interactions with giant planets on future orbits, even the subtle pressure of sunlight and outgassing forces could alter the comet's path in ways that compounded over millennia. C2025 R2 might return in 10,000 years, or 100,000 years, or never ejected from the solar system entirely by a close encounter with Jupiter, or captured into a shorter period orbit that would bring it back more frequently. The chaotic nature of orbital dynamics meant that precise long-term predictions remained impossible, but this uncertainty was itself profound. It meant that C2025 R2's appearance in late 2025 represented a unique moment in cosmic history, a convergence of trajectories that brought this ancient wanderer into human awareness during the brief flicker of time that defined our civilization's technological capability to observe and understand it. Humans had walked the earth for roughly 300,000 years. Anatomically modern humans with cognitive capabilities indistinguishable from our own had existed for, perhaps, 50,000 years. But only in the last few centuries had we developed the mathematics to understand orbital mechanics, the spectroscopy to analyze chemical composition, and the instrumentation to detect and track faint objects millions of kilometers away. C2025 R2 had been falling toward the Sun for potentially millions of years, but it arrived at precisely the moment when a technological civilization on the third planet was capable of recognizing it, studying it, and extracting meaning from its passage. That timing was either the most remarkable coincidence in the comet's entire existence, or it suggested something deeper, that perhaps the universe was more finely tuned for observation and understanding than we typically acknowledged. That consciousness itself might play some role in the cosmic story beyond mere passive witnessing. These were questions that transcended astronomy into philosophy, metaphysics, and existential contemplation. Science could describe what C2025 R2 was and how it behaved, but it couldn't fully address why its appearance felt meaningful to the humans who observed it. Perhaps meaning didn't require justification. Perhaps the sense of connection and wonder that came from watching an ancient visitor grace our skies was sufficient unto itself, a reminder that we were participants in something vastly larger than our individual lives, embedded in cosmic processes operating across scales of time and space that humbled even as they inspired. As C2025 R2 faded into the darkness beyond detection. It left behind not just data and publications, but a renewed sense of our place in the cosmos. We were not separate observers standing outside the universe looking in. We were the universe looking at itself, star stuff, contemplating star stuff. Ancient atoms arranged temporarily into forms capable of wonder, and that, perhaps, was the greatest gift any comet could bring.